Let's look at some of the reactions that we already know for making carboxylic acids. These are pretty much all of them are review reactions that we've already learned. We're going to start with oxidative cleavage of an alkyne, which was a reaction that you learned at the end of 241. So we learned that if we took an alkyne and we're going to make an internal alkyne, two different R groups on it, two-step reaction with ozone followed by water. We would break the molecule apart at the triple bond, and we would end up with two carboxylic acids. That's one method that we have. We learned, I think, at the beginning of 242, we learned the oxidation of primary alcohols. We can oxidize all kinds of alcohols, but only the oxidation of a primary alcohol results in the formation of a carboxylic acid. And we learned a couple different reagents that you could use to do this oxidation. But on paper, my favorite is sodium dichromate with H2SO4 and water. And this gives us a carboxylic acid, and it looks kind of weird the way I did that notation, but what I wanted to do was highlight the carbon of the alcohol that becomes the carbonyl carbon in the product, because it's pretty easy to add extra carbons or lose carbons in these reactions. At the end of 242, towards the end of 242, we learned about sidechain oxidation. This was a reaction that we learned when we were first getting introduced to aromatics. And we learned that if we had an R group, and it kind of didn't matter what the R group was, if we had an R group attached to a benzene ring, we could use our oxidizing reagents like sodium dichromate, and it would magically, regardless of how big that R group was, it would just shave the whole thing off down to a carboxylic acid group. So the size of the R group didn't matter. The only thing that mattered with this is that we could not have a tertiary carbon on the benzylic site. So the benzylic carbon has to have at least one hydrogen. At least, not one exactly, at least one hydrogen. So we could do sidechain oxidation with something like this. We could do sidechain oxidation with something like this. We cannot do sidechain oxidation with something like that, with tertiary benzylic carbon. And I noticed on sapling, they are using potassium permanganate for sidechain oxidation. That's totally fine. Works also and is definitely less of a carcinogen. We learned in I think it was in the last section of stuff that we were covering, the hydrolysis, or the last chapter, I think, the hydrolysis of a nitrile. This is a reaction that it looks super impossible, and this is one where the mechanism is coming. We are going to study how this reaction actually happens, but in the meantime, it just has to look like a mystery to you. So if we have a nitrile with some heat and a little bit of acid, you can convert that into a carboxylic acid, and it's not as crazy as it looks on paper. The nitrile carbon, carbonyl carbon, right? So be careful to not lose a carbon when you're doing that reaction. This is really easy to lose carbons in this reaction. At this point in your life, your eye is not trained to see the letter C as a carbon anymore. So it's super simple to make a mistake. Like somebody sees this guy right here, we'll say as an example, H3O plus, heat, and they go to predict the product of this reaction. At this point, your eye will see 2 carbons, and you'll just go like that. And that's wrong because you forgot about this carbon out here. There's actually 3 carbons in that molecule. So don't let that happen to you. And then last but not least, we have the carboxylation of Grignards. So this is not a new reaction completely. You've done Grignard reactions for a long time, but this is using a slightly different reagent in the Grignard reaction. So if we just take a regular Grignard reagent, and remember when we're using Grignard reagents, we're typically reacting them with carbonyl compounds like aldehydes or ketones or esters. You can also react a Grignard reagent with carbon dioxide. It's like the ultimate carbonyl compound. So you can react it with carbon dioxide, same reaction, same mechanism, same step 2, follow it up, and this will give us a carboxylic acid. You've got some carboxylation of Grignard problems on sapling, and some of the problems on there are going through the process also of reminding you where this Grignard comes from, just because it doesn't want you to forget. Grignards are formed by reacting an alkyl halide with magnesium in ether, and even some of the sapling problems are asking you questions about, hey, where would that alkyl halide come from? Like if you started with an alcohol, how would you convert the alcohol into the alkyl halide that you need to convert into the Grignard to do this particular reaction? So when you come across these problems, review your notes. This kind of stuff is in your 242 notes, converting an alcohol to an alkyl halide.